Hello students and welcome to a new lecture. We're going to be looking at the temperature and the solubility of the solid. Temperature dependence of solubility for several solid ionic compounds will be shown in the following diagram. If you can look at this diagram, you will see that for most salts, right? Most is the key word here. For most salts, solubility will increase with increasing temperature. But the reason why we say most, because it's not all. Some solubility decreases with increasing temperature. So when it comes to solid, most of them will increase solubility when I increase the temperature, but not all. However, if I look at the temperature and the solubility dependence of gases, we will see that for all gases, solubility will decrease with increasing the temperature. So the higher the temperature of the solution is, the less gas that can dissolve in it. For example, solubility of oxygen is reduced in water heated by thermal pollution, right? Because there is like the global warming thing, it's heating water, and the warmer the water is, the less oxygen dissolved in it, which really hurts the fish. Now, there is also a relationship between pressure and the solubility of gases. Henry's law states that the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. Remember how the gas will always be above a solution? The higher the pressure of that gas above the solution, the more of it will get inside and be soluble. So if you look at Henry's law, C, the concentration of the gas, equal constant times the pressure above that solution. So the higher the pressure, the higher the concentration. Concentration here is in molarity, mole per liter of a dissolved gas. P is the partial pressure in atmosphere of the gas over the solution. And K is Henry's constant, which is a constant that depends only on temperature. Look at this picture here. See how in the second picture we increase the pressure, right? And when you increase the pressure of the gas, more of it gets into the solution till you have a higher concentration of it. The higher the pressure, the higher the concentration. All right, now let's solve a problem about this. What is the molality of oxygen in water at 25 degrees Celsius for a partial pressure of 0.22 atmosphere? Henry's constant is 1.3 times 10 to the negative 3 mole per liter atmosphere, and density is the same as water. So clearly we have to apply Henry's law, which says that concentration equals Kp. What is it that I am given? I am giving the pressure, and I am giving K, which is a constant. I can find the concentration. However, concentration comes in molarity. So the first thing I can do is to get the concentration in molarity and then convert it into molarity, right? So I can say C equals K is 1.3 times 10 to the negative 3 mole per liter atmosphere, and the pressure is 0.22 atmosphere. I will do the math to get the molarity. So that will be 1.3 negative 3 times 0.22, 2 sig figs. So that will be 2.9 times 10 to the negative 4 molar. Okay? Now molality again is what, guys? Molality is number of moles over kilograms of solvent. So the moles is given from here, which is 2.9 times 10 to the negative 4. However, I'm going to have to find out the mass of the solvent. So the first thing I can do is finding out the mass of the solution, which is I have 1,000 milliliter solution from the definition of molarity. And the density is said to be as water, so 1 gram per milliliter. So that's going to give me 1,000 grams of solution. Then what you do next, as we have done before, you're going to calculate the mass that comes from 2.9 times 10 to the negative 4 moles of oxygen, and then say there are 32 grams of oxygen for every mole of oxygen. That's going to give you grams of oxygen. You're going to subtract, then you're going to have grams of water equal grams of solution minus grams of oxygen, and then you're going finally to calculate molality, which is moles of oxygen divided by kilogram of solvent. I'm not going to continue the math here because we have done plenty of examples here, and for another reason, because the mass of oxygen is so teeny tiny, right? It is not really going to affect anything here when it comes to the mass of water, and therefore in this case, after you do the math, you will find that they both have the same value. So molality and molarity will be the same only when you have a very small amount of the solute, and also because the density here happens to be 1 gram per milliliter. Okay, so that for this question here. Let's look at another question. You have a sample of water at sea level and another on top of Mountain Everest. Assuming that the temperature is the same, how would the amount dissolved in water compare between the two samples? Well, what will be the difference between the two samples here? Oxygen on the sea level has a certain pressure above water, and oxygen at the top of Mountain Everest, which is really high, will have a certain pressure. The pressure is going to be way less when you are highly elevated at the top of the mountain. Lower pressure, lower concentration of oxygen, lower solubility of oxygen. So at the top of the mountain, less oxygen will be on the water than it is at sea level. All right, that was it for this lecture. I will see you in the next one.